Hello, I'm Sugar Mike 6 Echo November Golf. In April 2016 I bought an SDR transceiver, a SunSDR2 PRO from Expert Electronics. The reason for my choice was that its architecture facilitates very good performance, and it also works on 2 meter on 144 MHz by use of undersampling. A friend of mine, Leif, Sugar Mike 5 Bravo Sierra Zulu, was kind enough to do some performance measurements on my SDR. Leif is a physicist who has made extensive contributions to the Ham Radio Society. He has under many years published a huge amount of articles and YouTube videos covering many topics. He has a profound knowledge about SDR, and he is the designer of the Linrad SDR. This measurement reveals that this SDR does not reach its full possible performance. There are design issues preventing it from being state-of-the-art. The impact of the design issues increases with increased frequency. On HF it's still usable, but on 144 MHz the performance is poor. Expert Electronics has unfortunately stumbled on the target line. The purpose of this video is not to present performance in exact figures. The purpose is to demonstrate how this SDR behaves on 144 MHz when it comes to signal handling capabilities. I have made some precautions to avoid misleading results. You can pause the video if you want to read longer. So now let's go to my laboratory. The entrance door is as usual blocked by my cat, Simon. The other cat you saw at the beginning of the video is named Svante. So I have to pause here and move my cat. Now we have entered my lab, and before starting the demonstrations I will give you a brief overview of the test equipment setup. Let's start with the signal generator. It's an HP8657A connected via this coax to an attenuator, 20 dB, further into a hybrid which splits the signal, the 3 dB split, into 2 outputs. This hybrid has a very good isolation, and the unused port is of course terminated with 50 ohm. One of the outputs goes further into a variable attenuator and further into my SDR. i.e. my device under test, the SunSDR2 PRO. The other output goes to another variable attenuator and further into my Icon 7400. The SDR is controlled by a laptop via Ethernet connection, and the used software is Expert SDR version 1.1.3, formally released version. Now the signal generator is set to plus 3 dBm, compensating the 3 dB split loss. And taking the attenuator on the input in account, that results in minus 20 dBm on the outputs. Now we can set desired signal level in the two receivers, and we start with a brief check that if we set the attenuator to 70 dB, we should have a signal level about minus 90 dBm, which roughly corresponds to S9. The definition of S9 of VHF is minus 93 dBm. So let's check on the S meter. You see the signal here, and the signal is fairly close to S9, which is accurate enough on the SDR. And let's go to the icon. It also shows S9, which is good. Those test equipments will be used in somewhat different configurations during the different demonstrations, but I will show you the exact configuration as block diagram, which is much more easy to follow. Finally, I used the preamps on both the SDR and the icon. I will now demonstrate how the SunSDR2 PRO handles strong signals. I used the test setup according to the following block diagram. Pause the video if you want to scrutinize it. I will now demonstrate how the receiver performs when it comes to handling strong signals. I put the receiver on 144.299.5 so I can hear the signal from the signal generator at 144.3. Using USB 2.7 kilohertz. And of course I can set the frequency exactly, but then you lose the signal. Now I will increase the signal level. As you see, I have adjusted it exactly now for S9. My attenuator used for that. I now increase the signal in 10 dB steps. You see this S meter increases. At S9 plus 20, some artifacts turns up, and I go up to S9. Sorry, that was S9 plus 20. Now it's S9 plus 30, and the artifacts or spurioses increases, and that continues. Now I have S9 plus 40, and there is a lot of them, and they're equally spaced around the center. Further, about 100 kilohertz out, there are some noise bumps coming up here, some broadband noise bumps. You can see it more clearly here. And now the noise floor also goes up, but that is highly likely from the signal generator, the signal sideband noise. And we will check that with my other receiver. But the focus now is those spurioses here. And observe that when I change the input level in 10 dB steps, that also is reflected on the received signal. Further 10 and further 10, and now it's S9 plus 60. So this is not a saturation issue. At, let's keep it S9 plus 40. These signals are about 20 dB over noise level. and about 70 dB down, and those are about 80 dB down. I will make note of some of those strongest bruises that we then use when I check with my other receiver. The LNA is on, and I can show you if I switch it off. I can, of course, turn the volume down. Most of them seems to disappear, but that is not the fact. They are hidden because of the raised noise floor. So if I increase the input from the signal generator again, they sure are there. So I switch the LNA on again. And there we are. And I keep this level S9 plus 40. I also want to mention that I have tried the dithering function on-off, I've tried the random on-off, and I've also changed the sampling rate. But this has no effect on the spurosis, they are still looking the same. So let's go over to my ICOM and look for those spurosis there. And I will select the strongest one below the center frequency. So here we go. Sorry, I have to move the camera a bit, etc. I turn the volume off. By the way, before that, I will just listen to one of those spurosis on my SDR before we leave it. So I set the step frequency 1 kilohertz, and then we can go. And here they are. I increased the volume, sorry. And they are a bit fussy, a bit noisy, but you sure can hear them. And I will go out to this noise bump here also. And that is also clearly heard in the receiver. So now move over to my ICOM. I have to turn on some light here. And now the attenuator to my SDR is set to, the extra attenuator is set to 29 dB. And I will also use 29 dB to my 29 dB to my ICOM. And now the signal strength is also S9 plus 40. I will now look for some of the spurosis that I wrote down in a paper and identified. The first one is 29225. spurioses there. The next one is 284.5. No spurioses there. 280.5. No spurioses there, and 276.5. Sorry. There are no spurioses. And I will go down for the noise bump to 220 somewhere. And to 190. And I don't hear the noise bump there. By this I have proved that the artifact is indeed created in the SDR. It's not something coming from the signal generator. They are not present in my ICOM. I mentioned earlier that the nature of this design issues are that the problem increases with increased frequency. So let's take a short look on 14.2 megahertz. I now connected my signal generator directly to the input of the SDR and set the signal level to S9 plus 40. And as you see, there are much less spurioses on the sides here. And I will increase the input a little bit further. That is S9 plus 50, and there are some coming up now. I mentioned that the software version is 1.1.3, but I forgot to show you information about the hardware. So here they are. I will now show how the spuriosis in the SunSDR2 PRO can affect your desired signal. I will listen to a weak signal, a beacon, and at the same time simulate a strong signal on the band by use of my signal generator. I can of course choose a long distance beacon with a weak signal, but there will be a lot of QSB on such signal which not is suitable for demonstration purpose. So instead I choose a stronger beacon that are rather close by, or 50 kilometers, and take down the signal level by use of an attenuator. This time I will use a slightly different test setup. The hybrid will not only be used as a signal splitter, but also as a combiner between the signal from the antenna and the signal generator. And the splitter will split the signal into my SDR and to my ICOM for comparison. You can look at the test configuration in this block diagram. Here is the antenna in HB9CV that I use for listening to the beacon. It's a very temporary installation, but it will do for this purpose. So now I will show the impact of a strong signal on the band when you're listening to a weak signal. I've chosen a beacon. In this case, it's SK6 VHF, and here it is. And I can take it is stronger, but I've taken the signal down. It's not that strong and not weak, it's good reliability. Now I will switch on my signal generator about 50 kc down. And I will also show you how the ICOM 7400 receives the signal later. So let's turn on the signal generator. There is a little bit of signal sideband noise from the generator, but it is sufficient for this purpose. The signal generator is here, and if I go set the frequency, listen to it, we can check that I set the signal level to S9 plus 40, and that is about 50 kc down from the beacon. So let's go back to the beacon. And now I will start to move the frequency of my signal generator and see how the artifacts affect the signal. So here we go. You hear that they are affecting the signal. And that is bad. Many say that 70, 89 dB down is not that bad, but if you consider the amount of spuriosis around the carrier, there are many possibilities that a nearby station causes interference. I move over to my ICOM receiver and check the impact there. I have to move the camera. I take the volume down on my SDR. And here is the signal. And it's not affected by the spurious. I will show you some even worse spuriosis. Sorry about the camera moving here, that's necessary. I go down to put volume up and approach the frequency of the signal generator. And you hear the character of those spurioses. They are not clean. I think there is. Now, if you will listen to a very weak signal, you will sure lose it. I go back to the icon. And there are no spurioses there. So that's a big difference. A good and sensitive waterfall spectrum is a very important tool for VHF and microwave operators. Unfortunately, the waterfall spectrum in the SunSDR2 PRO has some defects. First, it is not very sensitive. More averaging should be used. But worse is that it has blank points where you lose the signal in the waterfall. I'm now listening to my single generator and set it for a good signal S9 on 144.3 approximately. And you see the waterfall spectrum here. Now I will step my SDR frequency in I think it's 500 Hertz segment, and I will zoom in on the waterfall a bit. And you will see some very peculiar behavior. Now start stepping frequency. Just see the waterfall here. And I move the frequency. I move it. Move it. Back and forth. And suddenly it's gone. It disappears, and I move further. Comes back stronger. And I move further. Now it disappears. And I move further. And that's the case on both sides here. Here are points where you lose it. And this is, of course, a disaster. And interesting enough, I show you that the same thing happen if I resize the window size of the computer on the screen. So this is some sort of presentation problem. Now you see the waterfall clearly, the S9 signal, and I start to resize my window. And here it comes and goes as I resize the window. I might zoom in a bit again. And you see I resize the windows, and the waterfall comes and goes. Not only the present, but also the old information. I have, of course, addressed Expert Electronics about this, and they have acknowledged the problem and say they should be fixed in some later release. But that is soon 1 year ago, and nothing happens. So finally, let's take a short look on the transmitter side. I will use this configuration for this purpose. I'm now transmitting on 144.3 megahertz with 5 watts output. Checking on my spectrum analyzer with a span of 1 megahertz per division. The findings are these. You have 2 rather strong spurioses, about 45 dB below carrier outside the band, about 2.5 megahertz on each side of the carrier. And if we reduce the span to 100 kilohertz. You have two spur uses. It has to stabilize somewhat. Two spur uses about 400 kilohertz beside the carrier, and they are approximately 65 dB below carrier. And you have two further ones. They're about 150 kilohertz beside the carrier at the level of 70 dB below carrier. Let's go and listen for those spurioses on my receiver. It has to turn. I have set the signal level to, it's warming up, S9 plus 40. First let's check for plus minus 2.5 megahertz. That is 141.8. And there it is, about S8, which is corresponded with my spectrum analyzer. And the other side, plus 2.5 megahertz, that will be 146.8. There it is. Now for the spuriosus 400 kc from carrier, that is 143.9. And there it is, and 144.7, I guess, yeah. And there it is. Now I will make a further check a bit closer to the carrier. And we can adjust the frequency a bit on the spectrum analyzer. Go down to a resolution of 10 kc. Oh, whoops, I have to adjust. And there I have a resolution bandwidth of 300 Hertz to make it more sensible. You see, some spurioses turning out not fully symmetrical, but about 9 kc, from the carrier, and they are about 1, 2, 3, 4, 1, 2, 3, 4, 5, it's about 60 dB below carrier. So let's tune over the band and check if there are more spurioses to be heard. That was the familiar one. Let's go to the plus minus 8, 9 kc. And they are very noisy, fuzzy character. And on the other side, not a little bit further down, 9, 10 kc. Also very fuzzy, and they are similar to those ones that also are present in the receiver side, as I shown earlier. Now let's take a short look on the noise from the transmitter. I have replaced my spectrum analyzer, the HB8569B, to a E4448A. The reason for doing so is that this spectrum analyzer has much more dynamic range. I'm transmitting with 5 watts from my SDR through some attenuator, and then we set the span for 20 kilohertz per division, and the measuring bandwidth is 1 kilohertz. If we now look 20 kilohertz outside the carrier, we have a noise about an 80 dB below carrier, and that is approximately minus 110 dBc. And if we look 100 kc beside the carrier, we have approximately 90 dB below noise below carrier. That is minus 120 dBc. Now let's check the TX noise on 14 megahertz. We use the same setup for the spectrum analyzer, and looking at 20 kilohertz outside the carrier, we have a noise level of approximately minus 85 dB below carrier. That is 115 dBc, minus 115 dBc, and 100 kc out we have about 95 dB noise below carrier. That is minus 125 dBc. So the noise is less here on 14 megahertz in the transmitter, but it is also noticeable that the spurioses that we saw earlier are gone, so the signal is much cleaner here. I will now check the impact from the noise in the SunSDR2 PRO transmitter on a, so to speak, real signal. I'm listening to beacon LAH VHF, and I will transmit 20 kc down with a single tracer S9 plus 40. So let's check the impact. Transmitter on, transmitter off, transmitter on, transmitter off, transmitter on, transmitter off. And you can hear some impact of the noise. If I now increase the transmitting signal to S9 plus 50, and now transmit again, transmitter off, transmitter on, transmitter off. So here the noise is obvious on the beacon signal. I will now transmit 100 kc below the beacon frequency with the single tracer S9 plus 50. And we check the effect here. Transmitter on, transmitter off, transmitter on, transmitter off. So it sure has an effect even if I move 100 kc away. If I now had used the preamp and would be able to listen to even weaker signal, the impact of this TX noise would be higher. In the beginning of this video, I listed some precautions I made to get correct results. I will add one further precaution. As you see, I moved from the lab to my jack, and I have moved my SDR and connected it to my PC. In my lab, I use the laptop via an interface from USB to Ethernet. But now I use direct connection via Ethernet to my PC computer. And what I want to show you is that all the spurioses are still here, so that's nothing resulting from my computer. And here you see the spectrum, and you recognize all the spurioses. I have a signal level of S9 plus 40 from a coax coming from my lab. Now let's summarize this. To begin with, Sugar Mike 5 Bravo Sierra Zulu Leif did some measurements on my SunSDR. These measurements reveals that the SunSDR2 PRO does not reach its full possible performance. When compared with the Percev's SDR, which has been on the market for many years, it turns out that the Percev's SDR has better performance than the SunSDR2 PRO. This is of course very surprising, since SunSDR2 uses an ADC, analog digital converter, with 16 bits and a sampling rate possibility of 160 MHz, whilst the Percev's SDR only uses 14 bits with a sampling rate possibility of 80 MHz. You can look at Leif's measurements, which are published on YouTube. You find them under label SunSDR2. When you listen to signals that reach the level of S9 plus 20, 30, spurosis turns up. They are not that strong, they are about 70 to 80 dB below carrier, but there are many of them. This of course increases probability that they can cause problem. Since I read reviews stating that nothing comes close to SunSDR2 on 144 MHz, I of course have to check that the behavior is not unique for my unit. So I sent some measurement result to Expert Electronics and asked them to comment this. And the answer I got was this. And I quote, "This is how linear ADC LTC2209 works. Add some air noise and the issue will solve itself." This answer tells me that the behavior is not unique for my unit. It's common for all the SunSDR2 PRO units. But I'm not very satisfied with the answer, since it states that the problem will disappear if you add noise into the antenna. And of course, the spurosis will disappear if you add noise, but at the same time, you will not be able to copy weak signals. So I get the impression that Expert Electronics are not a very experienced VHF operator. My suspicions are enhanced due to the findings I showed about the badly implemented waterfall spectrum. And I will stress that signal levels of S9 plus 20 plus 30 not at all is uncommon on 144 MHz, especially when power amplifiers are used. And that goes for higher frequencies on the UHF and SHF also. And I'm sure that most of you have experienced this. I think the spurosis in the receiver are caused by jitter on the sampling clock. I have not scrutinized this further, since Expert Electronics does not publish schematic diagrams. The rather unpleasant, noisy and fuzzy spurosis, about plus minus 9 kHz beside carrier, present in both transmitter and receiver, can be caused by something else than jitter on the sampling clock. Now, however good receiver you have, that doesn't help if there are strong signals on the band from transmitters that transmit spurosis or high transmitting noise. I have earlier shown that the spurosis on the transmitting side is not that bad, It's much better compared with the receiver side. However, I think the noise level from the transmitter is a bit high. I'm fully aware that this is a very common problem for many transceivers on 144 MHz, but I had expected better from a modern transceiver. I'd like to mention that I have experienced some quality issues with my SDR. I lost output power on 144 MHz. The reason for that was a malfunctioning relay that switches the output signal from the DAC either to the HF amplifier or to the VHF amplifier. So I had to replace this relay. I finished this video by showing a list of my major findings.